Okay, so I'm hoping you're looking at my slides now. Joan, perhaps you can nod your head if everything looks good.
Yes, it looks good.
Okay, so I decided to bring two topics for my contribution to this financial engineering school, just to mix it up a bit, in the hope that some of the things I tell you may be useful or interesting, but they will be somewhat eclectic. So today I'm going to talk about backtesting. I've done quite a lot of work on backtesting of models of market risk. Recently, I've been working with Michael Gordy at the Federal Reserve in Washington on new methods for backtesting, and so I'm going to tell you about that. I'm going to integrate practical examples into my presentation, so there's going to be some R. I'll talk more about that later. On I think it's Tuesday, in 1 week's time, I'm going to talk about a different topic, which is the use of Coppola models. There is a link, which I'll make later on today, but next week it will be Coppola models. So let me give you a bit more context. My general interest is in quantitative risk management. I studied mathematics, I specialized in probability and statistics, and as a young postdoctoral student in Zurich, I became interested in applying mathematics to problems in quantitative risk management under the influence of Paul Embrechts, who was my boss in Zurich, and together with my colleague Rüdiger Frey, who's now at the Wirtschaftsuniversity in Vienna, the Vienna University of Business. And we wrote a book, actually the first edition was in 2005. We wrote about methods for market risk and VaR calculation. We wrote about methods for credit risk and about methods for integrating risk within a financial institution. And then after the financial crisis, we wrote a second edition, an extended and revised edition. And if you want to know more about what I'm talking about today, then this would be the primary reference. But I will be talking about more recent research that has appeared since 2015. Okay, so here's the overview. There will be roughly 3/3. I'm going to move at quite a fast tempo, certainly in part one, so that we can cover as much of this as possible in the, I think, just under 3 hours that we have. And first, I'll talk a little bit about the fundamentals of financial risk modeling. I will set the scene, talk about value, change in value, how we measure the risk associated with change in value. I'll say a little bit about the regulatory background for the trading book and market risk, and go over a couple of concepts in time series analysis, which will be useful in the examples. Then in the second third, we will get into standard backtesting methods. Although some of these methods will not be quite so standard. I think there will be things in there which, even if you're doing backtesting, you might not have seen before. So I'll talk about, for example, the topic of listability. And then in part three, I'll talk about recent research with Michael Gordy at the Federal Reserve on what we call spectral backtests, which use something called pit values. Everything will be explained in due course. Okay, so let me begin at the beginning and go into the first chapter. And the first topic really is to just give some notation and say what I mean by value and value change. So in my textbook, we wrote it for an audience like yourselves. So we wrote it for people working in risk in banks. We also wrote it for actuaries. You probably heard from my introduction. I'm currently a professor of actuarial science. And so I often teach very similar material to actuaries about risk. So the book starts with a grossly simplified balance sheet of a bank as well as one of an insurance company. And today I'm interested in the trading book, which is basically the red bit of this simple balance sheet. So you know that a bank, for example, the fictitious bank XYZ, like any company, has a balance sheet with assets and liabilities. Banks, of course, are taking in, well, not all banks, but sort of high street banks are taking in customer deposits. On the liability side, they may be funding themselves through bond issues. They have shareholders, so equity, but I'm interested in the left side of the balance sheet, and I'm interested in the trading book. So there is this division of the assets into the trading book and the banking book. The banking book is the loans and the assets that are generally held for longer periods than the ones in the trading book. And what I say today has to do with measuring risk in the trading book. So moving on probably quickly through these first few slides, the trading book, this is where you have your assets that are technically available to trade. In contrast with the banking book, which is where you would have the loans and other things that are not traded on a regular basis, but are usually held to maturity. And so if something appears in the trading book, then in theory, it should be easy to trade. It should be highly or relatively liquid, and it should be straightforward to value, to mark to market at any point in time. That's not necessarily true of everything in there, but in general, that's what you would expect. And so in the trading book, there will probably be a lot of fixed income kinds of instruments and more standardized derivatives, equity derivatives, foreign exchange derivatives. And we identify these kinds of instruments with market risk. And so there is a crude dichotomy between market risk in the trading book and credit risk being associated with the banking book and lending activities, although it is not as simple as that. So I'm not going to talk at all about credit risk today. That's a thing that I've done quite a lot of research on and a big part of my textbook, but I'm going to concentrate on market risk as it affects the trading book. Now, the Basel rules allow banks to use internal risk models to quantify their market risks in the trading book. As an alternative to internal models, there are standardized models, which smaller banks might use, or banks who don't meet the rigorous standards that are now imposed by regulators to use internal models. And these standards are more rigorous because the trading book was somewhat abused in the financial crisis of 2007 to 9. So many kinds of, in particular, securitized credit instruments were held in the trading book where they were subject to lower capital requirements, even though they weren't really, even though their purpose wasn't to trade, but more to be held to maturity. So let me go on now and just define some notation. The mathematics in my mini course today will not be too technical, I think, but from time to time, you're going to see some formulas. So if we think of the trading book as a big portfolio, then its value at any point in time is affected by what I call risk factors. And these risk factors are, for example, prices of equities. They are rates, foreign exchange rates, and interest rates for different maturities, depending on the nature of the fixed income instruments in the trading book, and also parameters that have a role in valuation, volatilities, for example, which have a role in valuing derivatives and which can be added to the collection of risk factors. And in my textbook with Frey and Embrechts, we spend a lot of time setting up a general framework for modeling everything in terms of risk factors. And we call the risk factors Z, or Z as the Americans would say, but I will call this Z. So Z is a vector of D risk factors measured at a point in time. The idea is that they can be measured at a point in time. They can be marked to market. And so the trading book is some kind of portfolio that depends on these risk factors. It has a value VT at time t, and this value depends on ZT. It also depends on time, because if you have products in the trading book which are derivatives, then the actual calendar time will be important because the time to maturity of the derivative will affect its current value. So that's why there's an explicit time dependence. This function f is called the portfolio mapping. We assume we know what we have in our trading book, so it's a known function, and the z's are observable. And we are interested in profits and losses. And to do the risk management and backtesting, I'm going to concentrate on the losses because we want to make sure that the bank is adequately capitalized to meet regulation and to withstand turbulence in the financial markets. So let's assume that the positions are held constant over a time step, which might be 1 day, but although it could be longer. So t to t plus 1 could be a time step. Then the trading loss, which might indeed be a profit, so it could be a profit, but the trading loss would be the negative of the value change over that time period. And inserting formula 1, what this is a function of the changes in the risk factors. So I've introduced in this formula a vector x, which is the changes in all of these risk factors from today to tomorrow, if we're looking at the next 24-hour horizon, or for the next week or for the next month, depending on the horizon. And so there is some functional, which I've called L here, and which in our book we call the loss operator, which basically tells you how a particular set of changes in the fundamental risk factors will drive the loss or the profit. So X are risk factor changes and L is a loss operator. But what I'm interested in today's part of the mini course is the distribution of L. So moving on, this is the essence of today's problem. What I want to do is I want to look at, actually it's a little bit inaccurate to say that I will estimate the conditional loss distribution. I'm going to assume that the conditional loss distribution has been estimated and then talk about how we test the quality of the model that has been used. So FT plus 1 is the conditional loss distribution. It's the probability that the trading book loss over the next time step is no bigger than X, conditional on everything we know. So at any point in time, we have data about the recent history of the financial markets. And so FT is basically the information available right now to us in order to make our risk forecasts over the next period. And then the risk management group in the institution is going to be estimating risk measures. And I'm just going to pick out 2. I'll mention another one later on, but I'll pick out VaR and expected shortfall because these remain the cornerstones of banking regulation. You may have heard that the capital formulas are now based on expected shortfall as a risk measure, but much of the validation regime is still based on value at risk. So these 2 risk measures are both important. I'll say a little bit more about their different roles very shortly, but they describe the tail of the conditional loss distribution. VaR is actually a quantile, and expected shortfall is a kind of expected tail loss. In fact, it does have other names. Other people might know it as tail conditional expectation, or some people call it CVaR, conditional VaR, but I will call it expected shortfall, and I'll define it very shortly. So we're interested in risk measures that describe a conditional loss distribution. And the methods that are used in practice, if you're really interested in a conditional loss distribution, you need dynamic estimation methods in order to capture the effect of volatility on the risk of the trading book. But some methods that are used in practice ignore volatility. We tend to call these unconditional approaches. They treat what happens over time as a stationary process, and they basically just estimate the stationary distribution of the loss rather than the conditional distribution. And when I talk about backtesting methods, I will look in particular at methods which can detect whether a bank is properly modeling volatility and the conditional distribution of losses, or whether they are neglecting volatility and really just modeling the unconditional or stationary distribution of losses. For the group that models the losses, so for the risk management team, there are many challenges in how you model risk factor changes. Risk factors are volatile. I've already mentioned that word. They also tend to have heavy-tailed distributions. So this is very widely known. It's called a stylized fact. They are certainly not normally distributed. They tend to have a heavy-tailed distribution. There are also lots of them. So you have many risk factors. And another topic that interests me is dimension reduction in factor modeling as applied to trading book modeling. So often the dimension is reduced by the use of factor models, but I won't go into that today. And this function is also very non-linear because of the fact that the trading book contains derivative products. It's not a long only or even long short equity portfolio, which would be quite linear, but it is a very non-linear function of the risk factors. So that's a problem for the risk modeling team. And of course, there are a variety of methods that are used, parametric methods, but it's also very common to use historical simulation, which is a sort of bootstrapping method where you resample past values of risk factors and look at the distribution of losses under changes that you've seen in the past to your risk factors. So again, I'm not really going to talk about the methods that are available for making the forecasts. So I'm not really going to talk about historical simulation or parametric risk models. I'm going to talk about how we backtest the models after we have backtest the models that are being used. Right. Okay, so the part 1.2, you could say just a few words about these risk measures. With 250 participants in this presentation, I'm aware that it's going to be impossible that you all have the same fundamental knowledge. So for those who know these things from back to front, apologies if I labor them. And for those who don't know them, then hopefully at least you get a sense of what I mean. So value at risk and expected shortfall. VaR is just a quantile. And if we want to give a mathematical formula, if our loss has a particular distribution function f, then the alpha VaR is simply the alpha quantile of the distribution f. So f is a distribution function. If we invert it in general, we get the quantile function. And that is simply what VaR is. In our textbook, we don't use a -1 for the inverse. We use a left arrow, which is a generalized inverse, but we don't need to worry about that at all. So f left arrow is the inverse of the distribution function. And so VaR is a quantile at level alpha. Alpha might be 95%, it might be 99%. Those are typical values. Expected shortfall, on the other hand, can be thought of in two ways. The way we tend to define it is as an integral of the quantile function. So if we integrate from level alpha to level 1, the quantile function, so u is the level, and we divide by 1 minus alpha, we get a kind of average over the quantiles. And that's one way of defining expected shortfall. But if f is a nice continuous distribution function, so not a discrete distribution that would jump, but instead a continuous one, then perhaps a more intuitive definition of expected shortfall, it's simply the expected loss given that the loss exceeds the alpha VaR. So the alpha expected shortfall is the expected loss given the loss exceeds the alpha VaR. And a picture is worth 1,000 words, as the cliche goes. So this might be a loss distribution, and it's entirely fictitious. And I've drawn a distribution where In fact, the mean loss is negative. In other words, it's a position which makes a profit or is expected to make a profit because the mean loss is minus 2.4, but there is a probability of a loss, i.e. a value bigger than 0. And the red vertical line marks the 95th percentile. So there is 5% probability beyond it. And that value on the x-axis is the 95% VaR. And the blue value, the 95% expected shortfall, is basically the expected value conditional on being in the tail. So conditional on being above the red value, what's your expected value? That is the blue value. In this case, it's double or roughly double the VaR. So that's the risk measures. And I'm going to move on into a little bit about the regulatory background now. This I will go through at quite a brisk tempo, I think, because there's an awful lot that could be said about regulation, to the extent that we could get stuck here for half an hour talking about regulation and then not do any financial engineering. But at one point, I had a very good look at a document called the Fundamental Review of the Trading Book, which came out after the financial crisis, published by the Basel Committee. And this was the review of the current, at the time, standard for market risk in the banking book and the suggestion of improvements to make it more rigorous. And so banks still have a choice between either using an internal model or a standardized approach. And for any sophisticated bank like Santander, you're assuming this, but you're going to be on the internal models approach, where you use your own models to quantify certain parts of the market risk. Now, what has changed is that in order to be allowed to use an internal model, the process of approval is much more rigorous. So you have to, that's where backtesting comes in. You have to backtest your internal model and submit your results to the regulator. And the quality of these backtests must meet certain criteria. And if it does, then the bank is allowed to continue to use an internal model. So these statements at the bottom here are taken from the Fundamental Review of the Trading Book. So it says in that review, banks must conduct regular backtesting. I'm not going to go into P&L attribution. They are required to compare each desk's value at risk measure, calibrated to the most recent data, at the 97.5th and 99th percentile. So I'll just draw your attention to the fact it says desk. This calculation actually is done at desk level to work out whether the model for a particular desk, whether that's equity derivatives or foreign exchange derivatives or some fixed income desk, so whether that desk has a good risk model. And if any desk has what are called VaR exceptions, more than 12 at the 99th percentile or more than 30 at the 97.5th, then that desk has to revert to the standardized approach to measuring risk and calculating capital. Now, why would a sophisticated bank want to use the internal models approach? The idea is that that should be less punitive in terms of capital, because a bank knows its own risks, then it should be holding exactly, one hopes, the right amount of capital for its own risks, whereas the standardized approach must be one size fits all and therefore quite conservative. So the idea is that on the internal models approach, or the thinking is that that ought to lead to lower capital. And of course, a bank in general doesn't want to have too much of a capital charge imposed on it, because that acts as a brake on the kind of risk-taking activities it can indulge in. So I'm not going to go through this slide in detail, but at one point, for my own amusement, I took all of the, I'm that kind of person. So I took all of the formulas out of the Fundamental Review of the Trading Book and I put them on one slide to kind of catalog the calculation process that is used to come up with a capital charge. Because the way that this slide is read, the final formula where it says ACC, that is the capital charge for the trading book. And there are a whole series of calculations that you go through before you arrive at that capital charge. And just to pick out a few things, the capital amount is actually based mainly on expected shortfall. So in fact, banks have to compute a 97.5% expected shortfall for a period of a certain number of days, which I've called H1. But they then have to use a scaling formula. They calculate expected shortfall values for different time horizons. This is designed to take into account the effect of liquidity risk. So this complicated calculation in the second line is about mitigating the effect of liquidity risk by taking into account that it might take longer to sell or neutralize certain risks in the trading book than others. So things to do with credit risk, more complicated structured products that are still in the trading book, they might have a longer liquidity horizon. So there is a whole talk I could give you on this funny formula in the second line, but it's designed to take into account liquidity risk. And then there are various scaling procedures that are applied to the expected shortfall. So various scaling procedures. And then I'm going to jump to the fifth line, the fifth formula, because when you've calculated this charge based on expected shortfall, you calculate a running average over a period of time. You calculate a running average. And then a multiplier is defined. A multiplier is defined. And I've put the multiplier in red because it relates once again to backtesting. The multiplier is a place in the capital calculation where the quality of the backtesting results directly feeds into the size of the capital charge. So depending on the value of this multiplier, the charge CA will be bigger or smaller. And CA is the charge for desks that have been approved to use the internal model. But if a desk is not approved to use the internal model, then they're using a standardized approach. And then there are some other add-ons like a default risk charge. But I want to talk about the multiplier now. The multiplier. And so this is what the fundamental review of the trading book says about the multiplier. So the multiplication factor will be 1.5, but banks must add to this a plus, which is related to the ex post performance of the risk model. And this plus will range from 0 to 0.5 and will be based on the outcome of the backtesting of the bank's daily VaR at the 99th percentile, based on current observations using the full set of risk factors. So there is a traffic light system. So if you have no more than 4 VaR exceptions, and when we do the practical, you will see VaR exceptions. So that concept will become clearer if it's not already something you know about. But if you have no more than 4 VaR exceptions, the multiplier is at the lowest level. It's 1.5. But if you have more than 4, then the multiplier begins to ratchet up. So that if you have 5, it's 1.7. If you have 9 exceptions, it's 1.9. And if you have greater or equal to 10 exceptions, then the multiplier assumes its highest level of 2. And moreover, there will be greater regulatory scrutiny of the bank because it will be considered that the quality of the bank's overall model for the trading book is suspicious. There are too many exceptions. And so therefore, the multiplier of 2. Now, the difference between 1.5 and 2 may not seem all that great, but remember it's a multiplier. And 2 is 33 and 1/3% bigger than 1.5. So you could say that this change in multiplier represents an additional 33% capital that the bank has to hold. So going back here, it feeds into the charge for the approved desks. So you don't want a higher multiplier. A higher multiplier means more capital for the trading book. So therefore you want to avoid that. So therefore you want to have the best risk forecasting model that you can have to keep your multiplier at a reasonable level. Okay. So that brings me to a few more sentences that I've taken from the fundamental review of the trading book. So we are going to talk about VaR backtesting, and we're going to look at it with a practical example, but we need to do more because the FRTB, and this has been adopted in Basel III, says that additional tests are required, and it says they are required, so you have to do it, but it says they may include, for instance. So as far as I understand, and I haven't actually revisited this very recently, but as far as I understand, there is a certain amount of discretion about what additional tests a bank does, but they must do some additional tests. So testing, for example, could be carried out for longer periods than required for the regular backtesting program. So for example, 3 years instead of 1 year. So 1 year is the standard length. So these numbers that I showed you here relate to 1 year. You might wonder what's so special about 4 and what's so special about 10. It's based on 1 year of backtests. And if you're looking at the 99% VaR, there's a 1% chance on any trading day you have an exception. And so in a year of 250 trading days, the expected number of exceptions for a good risk model is 1% times 250 or 2.5. So 2.5 might be expected and 10 would be quite a lot. Okay, so you might look at a longer period, or you might look at tests using the entire forecasting distribution. That's what I'm going to do in part 3, using the p-value of the desk's profit or loss on each day. So what is the p-value of the desk's profit or loss? I'm going to tell you what it is. I'm actually going to call it something different, something more academic, more econometric. I'm going to call it a PIT value, which stands for probability integral transform. For example, the bank could be required to use and make available to the supervisor the following kinds of information. 2 VaRs, one at the 99%, one at the 97.5%, and a daily expected shortfall value at the 97.5, or they could supply the daily P&L for the desk and the p-value or PIT value on each day for each desk. So I'm going to have a look at this particular method here using PIT values. I think maybe we need to put mute on. So excuse me, Joan, maybe you can do the global mute. Yeah. Okay. Yeah. Thank you. And so we'll look at this method using p-values or PIT values. And I'll repeat this point here. The testing of portfolios should be done at trading desk level and bank-wide level. So there's quite a lot of backtesting to do in order to comply with model validation standards, which you must do if you want to continue to use the internal model for as much of the trading book for as many desks as possible. And if you want to have a capital charge that is efficient, not too large. Okay, so the final part of this first chapter, I'm just going to mention a couple of concepts in time series analysis which will be helpful when we look at the practical. So we won't go into this too deeply, and some of you might be very expert econometricians, and so this will be something you studied long ago and know very well, but it's just to make sure that we're all on the same page, and we can all have some understanding of the examples I show you. So just some concepts in time series analysis. So let's consider a financial risk factor, Z, and consider observations which are made at discrete time intervals. And for the sake of argument, let's say daily, because that's typical for trading book risk measurement, that the canonical time horizon is daily. And so XT is the change in the value of the risk factor. If the risk factor is simply an asset price, in fact, we would tend to take a log asset price. So if these were just index trackers or individual equities or something, then the risk factor might be the log price. And in that case, XT would be what's called a log return or a log difference in price, which is slightly different to a relative difference in price, but tends to be analyzed because of the dominance of the geometric Brownian motion model in mathematical finance, which would say that prices follow a geometric Brownian motion and therefore log prices follow a Brownian motion. So that's a convention to look at log prices and log returns. And when we look at time series of changes in risk factors or log returns of prices, then there are certain things that we tend to observe, and we observe them so often that we call them facts. We call them stylized facts because they are empirical observations, but they are reconfirmed time and time again, and so therefore they have attained the level of facts. And so, in fact, they have very low serial correlation, typically, the risk factor changes. Risk factors go up, they go down, they go up, they go down. And if you look at the correlations over time, they can be quite low, but they're certainly not independent, these risk factor changes. If you were to look at absolute changes, they would be highly correlated because of volatility, because large movements tend to follow large movements in a risk factor. The signs may change, so you may get a large up movement followed by a large down movement. And so if you just look at the absolute values, you find a lot of correlation caused by volatility. The other important fact, the changes in risk factors, they're not normally distributed. They have heavy-tailed distributions. Sometimes people call them leptokurtic. And let's skip the final point. For one of my examples, I will use a GARCH model, not because I believe it's the best model, but because it's pretty accessible and can mimic the kind of behavior that we see in real financial data. So it can be useful for reproducing this kind of behavior. So ARCH and GARCH models, this is slightly unfortunate notation because the first line, this is a different ZT, not the risk factor. Should really change this. So ARCH and GARCH models, they are created from innovations. So now ZT is what's called strict white noise. It's just another name for independent, identically distributed data with a mean of 0 and a variance of 1. Doesn't have to be normal, could be a heavier tailed distribution than normal. But the model we used for the risk factor changes, we multiply the innovation. So ZT is called the innovation here. We multiply it by a volatility, sigma t, and this sigma t in the ARCH and GARCH is a function of the history up to time t minus 1, which is what we previously called ft minus 1. And moreover, the squared value of sigma t squared, the squared volatility, is simply the conditional variance of the risk factor change. And so in other words, volatility is the conditional standard deviation. Depending on time horizon, we might add in a mean term. So we might add to xt also a mu t, which depends on the past. If there is some predictability in the direction of risk factor changes over short time steps, we may model that explicitly, generally with ARMA type models. We can also do that. But just to finish this first chapter, In the ARCH model, the sigma t squared, which is the squared volatility, is a linear function of previous squared values. And so what happens here is if you have large risk factor changes in the recent past, let's say the last p days, because the memory here is of size p. If you have large values in the recent past, then they will influence the volatility and cause it to be higher. However, ARCH is very seldom used because the generalization, GARCH, incorporates some additional terms and tends to work much better. So sigma t squared, the squared volatility, is now a function of previous squared values, but also a function of previous squared volatilities. And by doing this, we can model longer memory in volatility, more persistence, as they call it in the econometric papers. Okay, so that's just in case you've never seen them. And now I'm going to make a little digression just to break things up a bit. And I'm going to go over to R. So I'm going to escape from the slides, and I'm going to show you another window. So let's have a look at this. So now you should be looking at something which looks a lot like computer code. And this is your practical for the day. And what might be interesting is to do a show of hands at this point. I'm not sure I can see the show of hands, but you have in Zoom a reactions button. At the bottom of the Zoom window, there's a reactions button. And if you're familiar with R, have used it before, then you could put up your hand there, and that would, and Joan, maybe you could have a look and see how many people know it, because I can't actually see the reactions. There's quite a few hands going up. Oh, I can see the reactions. Good, so quite a few hands are going up. But if you've never seen it before, then here's my browser. It's completely free software. You would get it here at the comprehensive R archive. You can download it for your machines. As I said, it's free. And the other thing you would want to get in order to reproduce everything I do today, the other thing you would want to get is RStudio, which is a kind of integrated development environment for using R. It is also free if you take the basic version, which is all you need. You don't need to actually buy it. You can take the free version. And the RStudio would be where you run R. And this is RStudio that you're looking at. So what I have distributed to participants is what's called an R markdown script. And you can see what I've distributed. So if you have R installed in your computer and you double click on the backtesting RMD file, it will open up, and then you can knit it. So if you see, hopefully this is large enough. If Joan, if you feel that there are problems with visibility at any point, just break it and tell me. If you think
there are a lot of people that would like to talk about something. I trying to give the opportunity of talk, but it's not easy at all. At least one of the organizers of the Santander Bank, Eulogio Miquel, I suppose now he can speak.
Do you want me to try? Sean, I'm Amalia.
Yes, Amalia, what happened?
Here, you want me to try to lift the hand down and let them talk, reactivate the audio?
Yes, I am trying to
okay, let me try.
Co-host to Eulogio, but I don't know how
where is Eulogio? Just
I can do this. I think Eulogio can speak now.
Yes, he's co-host and he can speak.
He's co-host, but has to activate himself the micro.
Okay, I can.
Yes. I saw that. I had a message, but I don't know why.
So is it questions of understanding you would like me to answer now, or questions for the Q&A at the end, or are there any technical issues?
No, I have no question.
Eulogio, can you say what you would like to ask?
No, I have no question.
I think it's just because I asked them to put their hands up if they were familiar with.
No, I put my hands up because you asked for.
Yes.
For having the R, but
that's great.
It is not. It is not. I have a question.
Great. Okay, that's what I thought.
Sorry for the confusion. Sorry.
Not a problem. If anyone does have a question that they really need to ask as I go along, then maybe put it in the chat with urgent or something, and Joanne, you can tell me and I can try and answer it. But we should have time for a Q&A in the final 10 minutes.
We will have some minutes at the final for questions, okay. But in the chat, I don't find any question by now.
Good. Okay. Well, in that case, I'll continue if that sounds okay. And what I was saying was, what I've sent you, you can knit it. So there's a ball of wool, which I hope you can see, and there's a word knit. And so knitting wool. And if I was to knit what I've sent you, it actually runs this code, and it will run it very fast for me because I've already cached the results. If you do this, you'll have to wait longer. But what you'll get is you'll get this. You'll get an HTML script will open in a browser, and you'll see what I'm going to do today, including the pictures that will be generated and all the commands. And so you'll have a record of what I've done. It will take longer to generate than it has for me because I already ran it once and I cached the results. The first time you run it, it will be a bit slow. The second time it would be fast. But I'm going to break it down into pieces. And so I am going to work from a .r file and just show you a few things. So I use 5 libraries in this presentation. One is the excellent RU GARCH library, which is for GARCH modeling. One is the QRM library, which actually accompanies my textbook. And so these have to be loaded from CRAN using the install packages. So using the install packages command, you would have to install these additional libraries. And I'm going to use RU GARCH just to show you a GARCH model because we're going to use this for backtesting in the next part. So I'm going to use GARCH as a way of generating some data which behaves somewhat like financial risk factor data. It will have volatility, it will be heavy-tailed, and so I use a function called uGARCH spec. If this needs to be bigger, then please say in the chat if I should make this bigger, but if it can stay at this size, then you'll see a little bit more. And we'd specify a model for the variance, which is of standard GARCH type. The order is 1, 1. That relates to the P and Q on the slides. We could add an ARMA model for the mean, but we don't. And the distribution of the innovations will be student. So STD stands for student. So true spec means the specification that is the truth, because I'm going to simulate from it. I have to fix some parameters. So I fix a set of parameters which will work for this process. And for example, the degree of freedom of the T distribution is quite small. So it's very heavy-tailed. So when I set the parameters, I'm fixing the parameters. And then I generate a realization. And I'm going to make this realization of length 2000 here. And So there is this will consist of two parts. It will consist of a window size and a number of forecasts, which I'll explain later. But I take a window size of size 1000. I'm going to make 1000 forecasts in the end. And so the total length of the simulation will be the sum of these two, as you see here. So I set a seed just for reproducibility, and I generate data from GARCH. And the first thing I'm showing you is that's the path of the volatility. So the sigma, or the sigma t, that's the path of the volatility. So you see there are some periods towards the end where you get high volatility. There are other periods where you get low volatility. And the next plot is the accompanying time series. And you can see in this time series that indeed towards the end, it looks more volatile. It looks like we have market drawdowns, etc. Okay, so that's a GARCH model. And I'm going to take the data contains quite a lot of information. It contains the volatility as well. I'm just going to take the path of the process. And that is going to be what we use in our backtesting as the data in order to understand how these methods work. And the next thing I'm going to do, actually, I think I'll do that after we talk about the backtesting. So that at least gets us started with R. And at this point, I'm going to go back to the theory, and we will, so I'll put this back into full screen, and we'll go into chapter 2. And then later on, we'll return to the R and look at how the methods work. We'll return for chapter 2 and for chapter 3.
Excuse me a moment, Alexander. Perhaps you can say that everybody has all the slices, all your code with an email we sent this morning.
Yes, thank you. So yeah, if you haven't checked your mail this morning, so that's what I referred to. You have the PDF of the slides, and you have this markdown file which will reproduce all the analysis, assuming that you have R and assuming that you first install the extra libraries which are listed at the beginning. Then it would all work. So as an introduction to backtesting, what's it about? So it's the practice of evaluating risk measurement procedures by comparing out-of-sample estimates with actual realized losses and gains. So we can make a forecast, let's say for the next day, using our risk model, and we can make a forecast of VaR for the next day. We can make a forecast of expected shortfall. And after 24 hours, we can compare with what is actually realized. We have a realized value of the P&L. And so by doing this over a period of time, we can look at this question of whether a given procedure is producing credible estimates of the risk measures. Does our procedure produce reasonable VaR values or not? Does it produce reasonable expected short values? So I think I've already said this. We make a forecast for the next period. At the end of the next period, we can compare. And this can be repeated over many time periods to monitor the model performance. Okay, so back to notation. So recall that the trading loss over a time interval is some complicated function of risk factor changes. So the actual loss is some complicated, typically nonlinear function of the risk factor changes. And we're interested in the conditional loss distribution. I'm not going to be precise about filtrations and sigma algebras. F here, we'll just think about it as the information that we have at time t-1, and which allows us to make a forecast for time period t. So in fact, I've actually moved the time step back one. In the first chapter, I talked about this is time t, and we look forward to time t+1. It's a little bit more convenient for the backtesting to say that for every time period t, we make a forecast at t-1, and we evaluate the quality of the forecast or compare it at time t. I will denote the alpha VaR and the alpha expected shortfall of this distribution by VaR alpha t and ES alpha t. And this is the true distribution. So this is the true conditional loss distribution, which I'm never going to know. In practice, I'm never going to know what this is. In a simulation, I know it. That's the beauty of a simulation and why we're going to look at the quality of the methods in a simulation. In a simulation, I know it, but in practice, I don't know it. And so I'm only ever going to see one observation from this distribution, and then life will move on, the markets will move on, and I won't see any more. So I'm going to have to, as a risk manager, I'm going to have to make a model for FT, and then I'm only ever going to see one observation from FT. So the risk modeling group at the bank, they form an estimate, a forecast distribution, and we call that one FT hat. So we use standard statistical language whereby a hat denotes the estimate. And so that's what's used for forecasting. And this estimator, well, there are so many options for what how this distribution could be created. It could be a parametric method, or it could be a non-parametric method. The historical simulation method, which is extremely widely used in practice by probably 75% of banks, if not more, is actually a non-parametric method using resampling or bootstrapping of past data. So it could be such a distribution, or it could be something parametric using a Monte Carlo method. And if we have estimated the distribution, then we can use that to estimate the value at risk. So that's VaR hat, and we can use it to estimate the expected shortfall. That is ES hat. So let us now look at how those would be backtested. So that is the basic setup. And how would those be backtested? So the event that LT, which is the true realized loss, exceeds VaR, that is what is called a VaR exception, or a VaR exceedance, or a VaR violation. There are at least three words that are used: violation, exception, or exceedance. But it's when the realized loss exceeds the alpha VaR. This event here is a theoretical valuation, because VaR alpha t is, or a violation of the theoretical VaR, because VaR alpha t, if I go back, that was the quantile, or the conditional quantile of the conditional loss distribution, which we don't know. There is a true one underlying the data, but we don't know exactly what it is unless we've simulated it. So this is the theoretical VaR. And if we look at the indicator of the event that the loss exceeds the VaR, that is a 0-1 variable. So IT is 1 if there is an exception, or it's 0 if there is no exception. And the conditional expectation of IT, conditional on past information, that's just the probability of a VaR exception given past information. By definition, that is 1 minus alpha. If VaR alpha t is really the alpha quantile, this probability is 1 minus alpha. And so you can write it in probability form, or you can write it in expectation form. In expectation form, we can introduce a function, which is a function of the loss and the VaR. It's called an identification function. And the actual function is written here in formula 8. So H alpha of the quantile Q and the loss L, we have the indicator that the loss exceeds Q minus 1 minus alpha. And so basically all we've done is we've written formula 7 by taking 1 minus alpha to the left-hand side. We've written it in the form that an expected value of a function of VaR and the loss, given the information we have, that this equals 0. Okay. Now, it can be shown that this holds, 7 holds, if and only if the sequence of indicators follows an independent, identically distributed Bernoulli process. That's often called a Bernoulli-Trials process. So this is equivalent. Formula 7 is completely equivalent or mathematically equivalent to saying that the sequence of indicators is an IID Bernoulli process where the probability that the indicator is 1 minus alpha. So the probability of an exception is 1 minus alpha. If alpha is 99%, this probability is 1%. So that's the meaning of a Bernoulli trials process. And that is testable. So that is a property of these exception indicators that we can test. And that's the basic idea of backtesting. So here are the two testable properties of a Bernoulli trials process. If we sum the violation indicators over time, then we get a binomial random variable, because independent Bernoulli variables, independent identically distributed Bernoulli variables, when added together, they give a binomial random variable. So if we do this over m equals 250 days, we get a binomial distribution where m is 250 and where the probability of an exception is 1 minus alpha, for example, 1%. So that is the first testable property. The other thing that can be tested is the independence property, because if these Bernoulli events are independent, then the waiting times between exceptions have a geometric distribution. So when you do elementary probability classes at school or university and you first learn about discrete distributions, you certainly learn about the binomial, and you probably also learn about the geometric. So if you're tossing a coin, the distribution of the time you have to wait until the next head pops up, for example. Well, it's similar for the backtesting, except that it's a biased coin where there's a certain probability of an exception, say 1%, and the converse probability of no exception is 99%. But if we define S to be the spacing, so S is the difference in time between violations. So the capital T's are the times of the violations, the capital S's are the spaces. These spaces should be independent, geometrically distributed random variables. And moreover, the mean of that distribution should be 1 over 1 minus alpha. And that can also be tested. And two remarks about this Bernoulli process. Backtesting is inherently a discrete thing. So you either get an exception or you don't. So that's why I call this a Bernoulli trials process. But when this is a small event probability, as it typically is in backtesting, then the Bernoulli trials process can be more or less considered as a Poisson process in time. And the geometric distribution can be approximated by an exponential distribution. So you can actually pass between methods which are defined for Poisson processes and exponential waiting times to methods for Bernoulli trials processes. Right. Now in practice, we estimate VaR. We don't know it, we estimate. So in practice, we have a sequence IT hat, which is the indicators that the realized losses exceed our estimates. So we don't actually know VaR, we just estimate it. But we would like our sequence of estimators to have the same property. We would like, ideally, that the probability that our estimate is exceeded, given all the information, is 1 minus alpha. And if that is true, then the sequence of indicator variables would be a Bernoulli-Charles process with probability 1 minus alpha. So basically, we form the empirical process of indicators, and we test whether that empirical process behaves like a Bernoulli-Charles process with probability 1 minus alpha. And so we can test the binomial behavior, and we can test the, we can also test the geometric weighting behavior. And standard backtests are particularly based on this binomial idea. So there are a number of classical tests of a binomial distribution. You can conduct likelihood ratio tests and other tests which are called score tests or wall tests. They're all very similar. And they're all based on similar theory. And my textbook has a number of references to standard statistics texts which go through these generic binomial tests. Suffice it to say that the traffic light procedure that I showed you earlier, so if you remember, the multiplier in the trading book is based on the number of exceptions, and there's a green zone, an orange zone or an amber zone, and a red zone. So if you have up to 4, it's green for good. If you have up to 10, it's orange for a little suspicious. And if it's red, then that is very suspicious. And that traffic light system has been set by using a binomial likelihood ratio test, actually by using the p-values of a binomial likelihood ratio test. So the Basel rules are based on a binomial likelihood ratio test. In my opinion, the binomial score test is a little bit better. It's very similar, but it's a little bit better. The geometric spacings or the exponential spacings, because when alpha is large, like 99%, it's very similar. That can be tested with a numerical test or with a QQ plot, which we'll look at. And in the literature on backtesting, there's quite a lot of papers. So a number of tests have been proposed to test for binomial behavior and also for independence. And one test that's very widely used is the Christofferson test. And the Christofferson test actually tries to test for both binomial behavior, so a binomial number, and also for independence of the violations. And it does that by testing against an alternative hypothesis that the violations or the exceptions behave like a Markov chain. So it tests against Markov chain dependence in the exceptions. It's not the most powerful test, but it is widely used, and therefore I will also implement it in the practical example. Just a little bit about terminology. If a test tests jointly for the right distribution, which is binomial, and for independence, we tend to call it a test of conditional coverage in econometrics. But if it only tests for distribution, we test for unconditional coverage. So where you see test of unconditional coverage, the test is only sensitive to a misspecification of the distribution. But where you see test of conditional coverage, the test is supposed to be sensitive to both a misspecification of the distribution and a misspecification of independence. So in fact, the data show signs of serial dependence. And so I'm going to talk about both those things in the remainder of my class today. Okay. Now, it might not be a bad idea at this point, I think, to go back to the practical, because I rather like to see things at the same time as I quite like to see the practice at the same time as the theory. So I'm going to go back to my previously prepared R scripts. I've broken it into two parts, incidentally. So you have one markdown file. I have broken it into two parts. So we have some real data X. So if you remember, and you can probably see in the bottom of my screen, I've just typed length of X. We have, and I'm going to type TS plot of X as well. That's my data, 2,000 of them. And I'll pretend that I don't know exactly where they come from at the moment. And so I am now a forecaster. I'm a forecaster, and these are trading book losses, and I have to forecast trading book losses, and I have to estimate VaR, and I have to estimate expected shortfall. So I'm going to set up two false specifications. So let's say that the trading book team, they get the right kind of model. So they use GARCH. So that's actually a good call or a good guess. So they're going to use GARCH. So in fact, the variance model is the right one. But what they're going to do wrong is they're going to misspecify the distribution. So instead of using a student distribution for the noise that drives this process, they're going to use a normal. And a normal has lighter tails. So this was the true one, student, in true spec. But this is a false spec. So a false specification because it has the wrong distribution. Now another team has a go, and this team also gets it wrong. This team, in fact, is too lazy to model the dynamics. And so when it says here GARCH order 00, that actually means that I switch off the GARCH model. There is no attempt to model volatility. The second team ignores volatility. But they actually work with a heavy-tailed distribution, the student, which is not so bad because, in fact, the data here are heavy-tailed. One way of seeing that is if I do QQ norm. I don't know if you know what that is, but that's the command that gives a QQ plot. The QQ plot of data is a plot of the quantiles of the data against the quantiles of a reference distribution. In this case, the quantiles of a normal distribution. And when you get an inverted S shape, so this is a kind of inverted S, then that is a very good sign that the data have a heavier tailed distribution than the reference. And that's what we see here because the data, I'm looking at a normal reference distribution and the data are much heavier tailed than normal. And a student might be capable of modeling that. So the second team uses the right kind of distribution, but no dynamics, so no volatility modeling. The third team guesses correctly, and so they're going to use the true specification, the third team, but they don't know the parameters. So only, I don't want to be blasphemous here, but only God or some oracle knows the parameters. I know them because I made the simulation, but in order to do the forecasting, the third group uses the true specification, but by assigning NA. So NA means missing value. So basically, instead of putting in values, which are correct, I put in a missing value and that removes the true parameters. So I'm going to set up the false spec 1 and 2 and the true spec. And here's how forecasting is going to proceed. It's going to proceed in a rolling manner. If you want to read about this, incidentally, did I compile it? I'll just knit that again. I'll just show you what you'd be able to read if you want to, if you having difficulty following anything I say, then there's a bit more detail in here. So the description of the setup of the forecasting models. And now I'm going to explain the rolling estimation procedure. So I've written it down, but let me go back to my script. So each group does a forecast. So group 1 is going to do a forecast with the wrong model. Group 2 is going to do a forecast with the wrong model, a different wrong model. And group 3 is going to do a forecast with the right model, but they still have to estimate everything. And so that's why you see that this uses the, sorry, I got it the wrong way around. Group 1 is using the true model. I beg your pardon. Group 1 is using the true model. Group 2 is using the first wrong model, and group 3 is using the second wrong model. And they're always forecasting one step ahead, okay? And they are going to carry out 1,000 forecasts. And each time they do a forecast, they're using the previous 1,000 days. So that's the idea of the window. The window is 1,000 days. That's the data that's used in order to make the forecast. And we'll make 1,000 forecasts. So that's the reason why I took 2,000 days of data, because I want to take a moving window of 1,000 and I want to move it over time. I don't know which way time goes for you, maybe it goes that way, and forecast one day ahead. But in order to speed things up, I'm only going to re-estimate the parameters every 5 days. I could re-estimate them every day, but refit every means I just re-estimate them every 5 days. So I'm going to set these going. I should have started that already, because this takes a few seconds. Let me just tell you about my setup here. So I'm just using an iMac computer in my home, and I am using the plain vanilla version of all functions. Some of these functions can be parallelized to work faster. And so much of this can be done much faster on more powerful machines and using parallelization. But I'm just going to do it in a plain vanilla way. And the first roll is now done. So that's and now I'll do the second roll for the second group. And what we're going to go on to do is we're going to have a look at what comes out of that. We're going to have a look at the VaR violations, and we're going to test their binomial behavior. We're going to test whether the number is consistent with a binomial distribution, and we're going to test whether the spacings are consistent with a binomial distribution. So the second roll is complete. The third roll is now in progress. So why roll? It's a rolling estimation. The window rolls through time. The window of data rolls through time, and we make a one step ahead prediction at every step. Okay, so the third roll is busy happening. Gives me time to take a quick drink. This library was written by so if you want to find out more about these packages in the RStudio, you can actually have a look at the package documentation. So I'm looking for RU-GARCH because that's the one I'm using. Excuse me, yeah, there's RU-GARCH. So this is a package for univariate GARCH models. There is one for multivariate. And in the description file, you can see it's written by someone called Alexios Galanos, who works for a hedge fund in America, I do believe, but has written this fantastic library for GARCH-based methods. So what do you see? Let's look at roll 1. Okay, so the call seemed to drop. Any of the organizers there?
You can start the questions now, or?
Yeah. Oh, yeah. It's
Or-
10 2. It's 10 2. So, yeah. So let's. Yeah. So it would be a good. Okay. So this we can pick up. So in a sense, we can keep the suspense as to what's going to happen. So I'll just reshare my screen. So, and I'll just wrap up. I'll go through what results we get in the next session, and continue to add to this analysis. So we'll keep the suspense about what's happening. And as Joan says, this is now the time we have 10 minutes for questions about the first part. So I'll keep sharing just in case there's any slide that I need to refer to, but I'm more than happy now to take questions.
Now, people who ask questions, I cannot activate his micro, but only I can give the possibility that himself activate his micro. And that is what I will do. I activate the possibility of activate him or herself, the micro. Then by now, I only report two questions that people ask. One is how can activate R, and the solution, of course, is R is free software that everyone can activate. The other question I report is what happens if you have exactly 10 values that are VaR exceptions?
I think that must relate to this question. I think this one relates to this question here about VaR exceptions. Yes, so 10 is the threshold for the largest multiplier. So I'll just reduce that. With 10 or more exceptions, the multiplier applied to the capital is at its largest level. Moreover, that probably is going to create some interest from the regulator as to why there are so many exceptions. And if you're wondering about these values 4 and 10, they are actually based